Welcome back to UBCCS 532W, Graduate Probabilistic Programming. Today is lecture 19, and we're going to talk about model learning. Okay. So, where have we gotten? Quite far, actually. So what have we covered? We've covered the programming language design space, Fobble-Hopple. We've covered inference algorithms, and we started talking about amortized inference last time in the form of inference compilation, or as you will see, the sleep phase update of the Helmholtz machine. Today we're going to start talking about model learning, which starts to bring Prob Prog into alignment with deep learning, in particular deep generative modeling, and it's sort of where it's at. The slide styles are going to be a little bit different. I apologize. So I'm throwing together some Beamer slides. There's going to be a lot of text on the slide, so different style, but we'll get through it anyway. So yeah, what have we assumed to this point? We've assumed there's a program in which we wish to perform inference, and it's fully specified. This is this Zubin diagram that we were talking about last time, right? So we've got a fully specified model, full or part, and then inference is slow and fast. Okay, so we know that there's lots of situations in which you have a fully specified model. Either you have a simulator or you're doing some sort of traditional Bayesian statistical analysis. And in those situations, often you only have one data set and you don't particularly care how long it takes for inference to complete, because you're only going to do inference once per program. And we want the highest possible inference quality results, blah, 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 blah. This lecture is going to push past this, okay? And I want us to think about this by considering a couple of example programs / applications. So here's a program we can look at, and there's a couple of ways one could write this. This is a hypothetical program. I don't actually have this program written anywhere, although it's close to your Bayesian neural network. All right, there's some procedure which samples weights for a neural network. There's some neural net architecture which does some sort of layer-wise, whatever computation on some given set of some input given some particular weights. We have a large data set, which just for convenience, we're just going to say is inline to what we know from the Hopple context. We could read it from a file. So we've got, input, label, a bunch of them. This is the number of training pairs, which we're going to assume is big. And then we have the weights for the neural network. And as you've seen, for each n, we can grab one of the y's. We can get the labels, and then we can observe under a discrete distribution the neural network observe the label given the parameters and the input. Cool. And clearly, straight away, there's a a fun issue here. This could either return theta, or it could return neural network theta evaluated on some test input.
So I just wanted to ask to check, we know a distribution for the weights? Like we're able to just generate samples for the weights?
So there's a couple of ways one could write this. So yes, we often know a distribution for the weights, particularly if you use weight decay or regularization. So this would just be an L2 norm on the weights. In other words, normally distributed, just like in the homework, right? IID normally distributed, or that was what we'll get to in just a second. We could just say these are, def param theta, in which case we put no prior on them, and they're just parameters. Okay, and we're going to see that these two things come into alignment in just a second.
So we can have the choice either we can put like a prior on the weights.
In what we've done so far, you have to put a prior on the weights, right?
Okay.
All of the programs, all the homeworks in which you've done Bayesian neural networks, if you actually go back and read the programs in which you've done inference, you will see that there is a weight decay prior on the parameters of the neural network. Okay, yeah, this is the question, and I actually would like to have a little debate about this, and we'll see how many statisticians we have in our mix, right? So should we, in this particular case, treat theta as something for which we do posterior inference? Or should we treat theta as a parameter for which we do maximum likelihood? So in other words, should we do point estimate? Or should we treat it as a latent variable?
Theta is the weights, right?
These are the weights, yeah.
Depends how much data you have.
Oh, nice. Why?
Because if you don't have a lot of data, then the point estimate's not going to be very good.
Yeah. Okay. Interesting. Yeah. Anybody else want to chime in here? Okay, that's the intuition that we're going for. Also, just to throw this out there, although this is a kind of a not a great example of this, one view of what's going on in this program, right, is that although it is a mod, that we have data, right, we have, X's and Y's, there is some neural net which is parameterized by theta, which is this link function, right? And we actually don't know what this is, right? So we have a partially specified program for which we want to do model learning, right? That's the definition of model learning. So this happens to be a conditional probability density, fine, whatever. But it's a model learning example, and we'll see why in just a little bit as well. Ping me later if that doesn't make sense. So we can think of this neural net function again as an otherwise impossible to code program fragment, right? Some part of the model which we'd like to learn. Okay. Here's another program. Unfortunately, I've given away what it is in the title. This is a variational autoencoder, right? So this would be familiar to you, hopefully, but if not, we'll make sense of it in just a second. This is a very general purpose model, which says xn, yn. There's a generative model, which says that we have some yns. There's going to be a bunch of parameters, and there's a latent variable x. Okay. So let's look at the generative model. So we have x and y here, right? So this says let x be a sample from some diagonal multivariate normal Gaussian, parameterized by theta. Then there are a couple of neural networks, hidden layer, a neural network that produces a hidden layer, a neural network that produces a mean, and a neural network that produces the variance of some diagonal multivariate normal with mean and standard deviation given by this. And we observe some data y. Okay. How many of you are not familiar with VAs? How many of you have no experience with VAs? Awesome. Okay, that's to be expected. Okay, so this is a bit of a weird model compared to what we've been looking at, in the sense that really what we're saying is we have somewhere a whole lot of y's, y1 to yn, right? And what we want to do is condition somehow. I mean, what do we want to do? One thing that we could do is say, okay, we could at the end here make the actual program just be have this return X. So this procedure actually return X. Excuse me, not X. Yeah. How to put this for those of you who are not familiar with VAEs in this context. Let me put it this way. What you want to do is density estimation about Y, right? But we're imposing a latent variable, and we are actually saying nothing. We have no idea what the generative model component is that goes in here. This is just some neural net link function. Okay. So from the context of the probabilistic programming systems that we've talked about, such a model is totally nonsensical because we have no ability to write down what this generative model is. It doesn't make sense. It's just some abstract neural network, right? However, if we want to do model learning, we might want to actually learn the values of this theta from some data. So in other words, if I have a bunch of y's and I want to learn a model of those y's, that's a latent variable model which has this x in it and is parameterized by theta, right? I have to come up with some sensible way of expressing model learning, first of all, and that's what we're going to talk about. And second of all, I have to decide whether or not I want to do inference over theta or whether or not I want to maximize over theta. And I have to, like the only thing that I'm doing in this model is making a structural assumption about the generative model for Y, which is to say that it's a one layer, some sort of deterministic transformation from some latent variable, okay? If you're unfamiliar, the next comment is like, how do you hand code a generative model for an MNIST digit? If you know pictures of MNIST digits, I probably don't need to draw it here. I have some vector of images. How do you write a simulator for that, a generative model for an image? Anybody want to? MNIST, what does MNIST stand for? The NIST stands for National Institutes of Standards and Technology, and then M stands for, I have no idea. MNIST digits, I should have put pictures of them in here, I guess. Can anybody drop the MNIST link on? Is that right? Modified? No.
That's what comes up on Google.
Really? Interesting. Okay.
Maybe you could just remind me what a generative model is exactly. I have like a vague sense, but
that's literally every single program that we've written in the Hopple, Fopple, or anything in the class. You start from latent variables and you go to observed quantities, right? Is the generative model of grass being wet, sprinklers, so on and so forth. Generative model of geometrically distributed random variables, generative model of sequence data, generative model of outputs given inputs in a neural network. Literally every single program that we've written has been a generative model.
Okay.
Okay. So if you have a generative model of an MNIST digit, thank you for those. Thank you. Great. So if you've clicked on those, everybody can see what the MNIST digits are. They're just pictures, right? So how do we write a generative model for one of these pictures? For those of you who did not put your hands up for that's really more for the people who didn't put their hands up when I asked about VAEs. So I guess I won't name drop you. Good old upsampling network. Okay, that probably doesn't make a lot of sense to people, but yeah, that'll work. Yeah.
So are you looking for a way to make a generative model without VAEs, or
Yeah,
is that the
I'm
question?
asking, like, how would one, yeah, anyway, so like, like, I just want to think about generative modeling. Like, how would you actually write a generative model for this data, right? We know how to write a generative model for sprinkler data. We know how to write a generative model for bag of words stuff that was LDA. We know how to write a generative model for sequences. How do we write a generative model for some complex data object like this?
Can't we write a generative model for neural networks?
We wrote a generative model for neural networks by putting an L2 regularization on the weights. That's a generative model for a neural network of a given architecture.
So don't neural networks do this whole digit recognize thing?
We're not doing recognition. We're doing generation.
Yeah, but we just reverse it.
You can't say train a VAE unless you know what the VAE is. So you just reverse it. Okay, so this is Payman's upsampling neural network, right? So what I'm saying, what I'm trying to get you to think about is that writing such a generative model is hard, right? Basically, the only way to specify it is as some partially specified program in the form of a neural network, basically in this form right here, the decoder. Okay, so just read this as a generative model, which is given some parameter. If you'd like, we can put, let theta be sample from L2, sample IID normal here. That's fine. And then we could, at the end of this, call generative model and then return theta from the program. Okay? So this would give us a posterior distribution on the model parameters in a generative model, which transforms a noise vector sampled from a diagonal MVN. In fact, usually this is just 0, 1 here. And passes it through a neural network whose parameters are unspecified but come in the form of theta, and then observes under a multivariate normal the digit. If the code is too much, we can say theta is drawn, normal 0 I, x is drawn normal theta, y in given x in and theta. Sorry. X in theta is drawn from a normal distribution parameterized by some neural network that takes x and theta, and some other neural network that takes x and theta. That's a weird generative model, right? It's a weird generative model in the sense that the entirety of the generative model that actually makes a digit is wrapped up in whatever these neural networks do. And what those neural networks do is given by the value of this theta. So you could write, just to be clear for those of us, those smarty pants in the course who already know what a VAE is, you can write a VAE in the languages that we've established already. In fact, you can write a VAE in the FOPL language very straightforwardly, and then use Hamiltonian Monte Carlo or whatever to learn under IID data a posterior distribution over VAE model parameters. Right? It's just a probabilistic model in which one can do inference. Right? The question is, do we do inference over the parameters of the VAE, or do we do point estimates It's the same kind of a problem. The only difference between this model and the other model is this is unsupervised. Right? You only have the data. You don't have the label in some sense, or maybe you can think of this as you only have the label, you don't have the input. And another way of saying it is that when we do maximum likelihood in this model, we have to integrate over this random variable. Okay. Hopefully this will become clear in a little bit. I sort of forget that the variational autoencoder is not part and parcel of everybody's pre-existing experience. Okay, so what's the point? The first point is, how do you hand code a generative model of very complex things? Right? You can't. That's probably the nastiest thing when you come from the probabilistic programming point of view, is that you start from thinking that you can write generative models, but in fact, for complex data, you cannot write generative models, right? You have to learn them. That's okay, right? Because we can still use the tools of inference to learn them. That's totally fine. We've always known this. That's always been the Prob Prog perspective. Just use inference to learn the parameters of the generative model, right? But as you have experienced in running non-sequential based inference methods for the HMM, inference is not always the easiest thing to do in the models that you have, right? Just straight inference is not necessarily so easy, and gradient-based methods work very, very well. More to the point, though, if you have latent variables like this, really you need to work a little harder. But anyway, variational autoencoder consists of a generative model, which transforms a random vector into a likelihood over some observation space. That's what I just showed you. And this amortized inference artifact, and we'll come back to the VAE once we get through all the other stuff, that performs approximate inference in constant time. The decoder part of a VAE is a partially specified generative model. Okay. Only the structure of the model is provided, just the architecture and the distribution types of the prior and likelihood. The rest has to be learned from data. But if you do this, you can learn how to generate MNIST digits very straightforwardly. Okay, cool. So learning parameters, like basically doing, and what I mean here is point estimates, in the way that Naomi pointed out from data, makes sense when there's a sufficiently large amount of data available. Okay. This is super common in modern machine learning applications. It's not the dominant, it's not predominant, but certainly for the FANG companies, it's true, where we have tons and tons of instances. So we can get tons and tons of instances of MNIST digits, 60,000 of them or so, right? We can get tons and tons of instances of photos and so on and so forth, where we can go off and try to learn models that generate those things. Model learning is required when all or part of the generative model program is non-programmable, or otherwise can only be partially specified. So this VAE thing, which I should have anticipated that not everybody knew, but I apologize, I stumbled over a little bit. The whole point is that it is an arbitrary generative, it's just this generative model, right? It's just theta x, y, like that. That's it. It's just a generative model, right? But it's only partially specified. It's only the generative model is only specified up to the neural net architecture. When either of these things are the case, when you have to learn the model, right, because of whatever reason, we set up model parameter learning in terms of maximum likelihood. Okay, and this is where I think Emma is going to be upset, because now we're going to recognize that the evidence is also a likelihood, and that can be a little bit confusing, right? So model learning we set up in terms of maximizing what is known as the marginal likelihood or evidence, right? And why do we call it marginal likelihood? Because if you think about what's happening, say for instance, in that VAE model, and we'll just look at a single instance for the moment. P of y given theta is equal to the integral of P of x given the, of the joint, P of xy dx. This is given theta, right? And when you're doing all of the marginal probability estimates in sequential Monte Carlo or so on and so forth, what you're computing is this marginal probability estimate. This is the same. This is the exact same thing that comes out of SMC, right? It's also the thing that comes out of importance sampling. We get a marginal probability estimate, right? Fine. So that's why we're going to call this is the evidence. It's the evidence that we compute in all of our inference algorithms, right? It's also the marginal probability of the data. It's also the likelihood of the data under the model. They all mean the same thing. Okay, fine.
Can I ask a question?
Please.
It's also the generative model. Is that right? Is that another thing that we can add to that list, or is that not quite correct?
And the generative model is the whole joint distribution.
Yeah, okay.
Right?
Okay, yeah.
This is the marginal probability of the data under the generative model, which requires integrating out the latent variables.
Yeah, okay.
Yeah. Okay, cool.
So do you obtain a generative model after you find theta star, or you can have one without like selecting a theta?
So theta, you can think of very directly. This is not think of. You can think of theta as parameterizing a family of models.
Okay.
Right. So for every value of theta, you get a different instance of a generative model. And when we do model learning, what we want to do is we want to find one instance of in this model class, in this model family, that describes the data well.
So then it's the first thing I said, which is that you get a generative model from a specific theta.
Theta indexes generative models. Yes.
Yeah. Okay.
Right. In this context, but again, it depends on where you define the boundary. If you put theta inside the model, then whatever. So, but right now we're going to be thinking about theta as being outside the model and indexing the generative model.
I guess if we had like a prior on theta, then it would be the other case, right? Then the generative model wouldn't depend on theta.
It depends,
Okay.
right? So like what's a prior, what's a hyperprior, what's a parameter, they're all fluid based on wherever you define the boundaries. Exactly, okay? Okay, cool.
Can I also ask?
Please, yeah.
I wasn't clear on what it means when it's partially specified.
So if you think about what a neural network is, right? So basically what Payman was saying for a VAE is we're going to have some latent variable X, and then we're going to have some compute. This is not a, let me make sure that you understand this is not a graphical model. These are discrete computations. We have to have some sort of what Payman would call an upsampling, or most people would call a deconvolution network, or whatever. There's some network that starts from a low dimensional space and then progressively builds larger and larger, higher dimensional vector. Basically, it has to at least build a mean vector, right? So there's a question of what is the shape of this computation, right? What is actually the structure of the computation? And then if there are parameters, weights and biases for each of these deterministic operations, right? Those also need to be specified. So there's a combinatorial aspect of the model, which is its computational graph. It's the structure of its computation. You're familiar with computational graphs from FOPL, right? Another way of thinking about what a computational graph is in this kind of thing, just to throw it out there. And I think I mentioned this in one lecture, but it's really important. And Ryan will nod his head when I say this or whatever. Is that if you replace every single deterministic operation in the model with a Dirac distributed quantity, then your FOPL compiler will generate the compute graph for the generative model. Okay. And you could imagine, and here's one for Mia because she likes program synthesis, right? You could imagine a generative model for generative models, which generates the structure of the model and the numerical quantities used inside that structure. That make sense?
So wait, is partially specified when we don't know the structure?
Partially specified is when you know the structure, but you don't know the numerical quantities that go into the structure. That's the way we're using it here. But partially specified just means that you don't know some part of the model. It might be part of the combinatorial structure, it might be part of the continuous structure or differentiable structure, it might be whatever, right? In general, in the examples that I'm giving right now anyway, in the examples I'm giving right now, I'm saying that you know the combinatorial part, but you don't know the differentiable part. But in general, in probabilistic programming, we're allowed to think about doing inference and learning over both types.
So this is not a graphical model that you drew? I was a bit confused by what the drawing is.
This is not, okay, great. So we have X. Let's say X is literally, this is X in a VAE. This is literally just normal 0, 1. Okay, and we have Y down here, which in the case of MNIST digits is 768 dimensional, I think. Is that right? So this is Y1, Y2, all the way up to Y768. Okay. We have to be able to get to a link function that somehow generates all of these. And we said in the VAE case, this is going to be normal with respect to some neural network that produces a mean vector. So there's a bunch of deterministic computation nodes. Who the heck knows what this looks like? I mean, actually, probably only Ryan really knows what this looks like out of everybody. But there's a whole bunch of deterministic computation nodes that lead to that produce the link function. This is a link function in the same way we were talking about before. It's just a link function, right? But it happens to be a neural network, and so in the context of your first homeworks up to, I guess, homework 4, you have the graphical model representation and there's a link function, right? That link function is either fully specified or it's not fully specified, right? And there are aspects of that link function that are structural, like what operations and what depth of operations, and then there are constants and numeric values that go into that.
Right, there could be like these activation functions that are like these linear functions, and they have like
so there could be some non-parameterized functions, like that could be a ReLU function, but this could be a plus bias function where it needs to have a bias node that comes into this.
And then the bias becomes like just a parameter.
Just a number. It's a parameter. Yeah.
Okay, I understand.
Awesome. Great. Cool. But the reason why, yeah, go ahead. Yeah.
So I was kind of trying to wrap my head around what is X exactly. So like in a like CAPTCHA example that we had way before, X was like, the true sequence of characters or something like that. But here, X is just sample from some like whatever distribution we want, and it doesn't have to correspond to anything. Like we can't choose like which digit this model would generate, right? It would just generate something at random, right?
That's 100% correct. All this is doing is it's building a density estimate. If you think about what does this say, right? This says there is some density that we'd like to match.
Okay.
Right. That's what a VAE is doing. If you happen to be semi-supervised and you happen to have labels for some of them, then you're in semi-supervised VAE land, and the kickoff for Pyro and that entire field of semi-supervised variational autoencoders came out of Prob Prog and my group and Noah's group and so on and so forth, right? So yes, yes to both. I think you understand. Yeah.
Okay.
It's a very weird. It's a weird thing if you're unfamiliar with the idea of transforming a noise variable to produce a density estimate, right? But if you think about what traditional random variable generators do, they take a random noise source and they transform it into some space that you want to model. That's exactly how, for instance, normal random variates are generated. You take a noise vector and you transform it into a multivariate normal draw or something like that. That's really all that's happening in VAE land. You take a noise variable and you transform it into some density estimate, right? Okay, fine, cool. All right, so the problem is we want to maximize this thing, or maybe we want to maximize it, right? So here we're going to switch and from doing inference, which we talked about, to doing maximum likelihood modeling. Okay, and the reason why we're going to do this is several-fold, right? So one is that if you just think about what's going on, for instance, if you have a lot of data and you have, P of y1 given theta, P of y2 given theta, P of y 1 million given theta, P theta, right? And we know that, P of theta given y looks like this. Clearly, when you multiply in all of these terms, first of all, the data is going to dominate. And second of all, you're going to get a very, in general, you're going to get a very sharp signal or peak on one of these thetas, okay? And formally what ends up happening is there's this beautiful theorem called the Bernstein-von Mises theorem, which we won't go into the details of, but basically it says under suitable conditions in parametric models, the limit of any Bayesian estimator in a parametric model under infinite data goes to the maximum likelihood estimator. In other words, the prior is forgotten. You stay in the same model family, but the prior is totally forgotten. So if you have enough data, then there's no point in being Bayesian because you have enough data. Okay. Now, if we go back, just to be clear, well, we haven't done this, but remember, there's a plate around. Sorry, there will be in the VAE case. And whatever, there's going to be a plate around this in the graphical modeling sense. And theta roughly is going to go in here. So this is data with respect to theta. So Bernstein-von Mises will apply to theta when we have a large number of observations. Or in the neural networking case where you actually have x and y, both. And theta comes in like this. This is data with respect to theta. So this is Bayesian neural networks, which sort of become non-Bayesian when you do invoke Bernstein-von Mises. And this is the VAE decoder or generative model. But the latent variable in the VAE decoder is the Bernstein-von Mises does not apply to that. Because that latent variable, there's one per data item, so you can't concentrate that, okay? All right.
I have a question.
Awesome.
About when you said the prior is forgotten. I'm struggling to wrap my head around what that means.
Okay, sorry, that was not a reaction to your question. It's me wanting to write down. I went back and forth about whether or not to write down like what Bernstein-von Mises says, but it says that in this model. Right, forget that there's a prior on. So like if we put a prior on theta, we can say this is an L2 norm prior or normal 0, 1. If we put a prior on theta, okay. if we're doing let's just do Bayesian neural network for just a second. If we're doing a Bayesian neural network and we have a small amount of data, our posterior distribution, as you've seen in the homework for theta, is going to move around a lot, right? There's going to actually be variance in the posterior estimate. Most of you have seen this in your homeworks, not all of you, but most of you, right? So there'll be variance in your posterior estimate. In other words, the posterior samples that you get of theta are going to move around, right? The first part of Bernstein von Mises says that as in the limit of data, the variance of the posterior goes to 0. That's the first part of Bernstein von Mises. So there will be no posterior variance at all because all posterior mass will concentrate on a point. That's the first part of Bernstein von Mises. The second point of Bernstein von Mises says that posterior variance collapses to the sampling distribution of the maximum likelihood estimate. So the frequentist uncertainty of the maximum likelihood estimator. So if you were to do maximum likelihood estimation, i.e. what you would normally do in a regression setting on theta, that's going to give you an estimator for theta. It's going to give you a point estimator. That point estimate is going to move around as well, right? And the sampling, like the frequentist sampling distribution of the point estimator and the Bayesian posterior distribution coincide. And we know that MLE estimators are consistent in the limit, which is to say that they will converge to a point mass at the true model parameter if the model parameters if the true data generating process is within the model space. So there's like 3 levels of convergence that happen. Bernstein von Mises says the posterior distribution goes to the maximum likelihood frequentist sampling distribution. The frequentist sampling distribution goes to a point mass, and the point mass goes to whatever the maximum likelihood estimate is. It converges to an atom with no uncertainty. Okay. You could teach an entire course on this. Like R. Vanderwaart has a whole book on convergent properties of asymptotic properties of Bayesian estimators. But it is the justification. It is the formal justification. You can invoke it basically anytime you want to, in a parametric model, go from doing inference to parameter estimation. Okay, cool.
Can I ask another question before we move on? In the 2 graphical models that you've drawn there,
yep.
Is it intentional that the theta did not have a circle around it first? Is that just like to mean that now theta is no longer has a prior on it, but we're using a point estimate for it? If you don't have a circle,
generally speaking, if you don't put a circle on it, it's not a random variable anymore. It's a parameter, right?
Yeah. So
it gets a little bit subtle as well, because when you're doing maximum likelihood or optimization, you often impose some sort of you often impose regularization in the optimizer, which is the same thing as doing map. So it turns out also that map and MLE and all these things, they all become basically the same thing in parametric models. So if you're the difference between maximum likelihood and map is just regularization, right? The difference between inference and optimization is you characterize a full posterior distribution or you do a point estimate.
Okay, but we're doing point estimates now, right? So
we're moving over to point estimates because we're assuming that we're in a big data regime where we can invoke Bernstein von Mises, and the posterior distribution over whatever model parameters would collapse to a point estimate in all practical purposes, for all practical purposes anyway. So we might as well just do parameter estimation pointwise rather than full inference.
Cool. Yeah, I'm with you.
Everybody else with me? Yeah, good. Okay. Yeah.
I'm 100%. Because, okay, so when I think of like the regularization, like the L2, I kind of associate this with having that prior that we discussed before, like the normal.
That's correct. You should. Yeah.
So then one of the like takeaways of this theorem is that, you know, with a lot of data, the prior becomes insignificant. But then when I think of these like point estimates, I think of them having these regularizers. So is it like, where am I thinking wrong? Like here I'm thinking like, okay, well, this like map is already has this like, I'm thinking a lot from optimization point of view. Like you want to minimize this, like you want to add this regularization term. So like it could be the L2. But yeah, so it doesn't really correspond anymore in my
Yeah, so I don't think it. I don't think the map thing does. So I think I probably misspoke there. I would have to go back and think about that. That's a good question. We're gonna have to come back to that to be 100% absolutely certain that map from the outside is the same as MLE versus inference here. That's actually pretty subtle. Provided that you're okay with the idea that we're going to be doing point estimates and that there is some justification for doing it, that's really where I want us to be. That's it. I intentionally didn't want to get bogged down on the details of these of Bernstein von Mises because it's a nasty rabbit warren of mathematical detail. So, are we okay with doing point estimates, whether you regularize them on the outside or not?
Yeah.
Okay. Good. Okay, yeah, so there's some caveats on Bernstein von Mises. We'll skip over that so we can get to the meat. Okay. So I've already said this, so maximum likelihood estimation for model parameter modeling connects to posterior inference, but let's just make this connection clear. The whole point is that we're doing maximum likelihood parameter estimation in the general case in models with latent variables. And in order to do maximum likelihood, in order to maximize this thing, we have to actually integrate out our latent variables. And again, you should be thinking program structured the entire time here, right? So the connection between posterior inference, sorry about the sirens, really becomes apparent when we think about maximizing the evidence via gradients, right? And the reason why is that we can express this gradient, the gradient that we need if we want to do gradient-based optimization of the marginal probability or gradient-based optimization of the evidence with respect to the model parameters. We can express this as an expectation over the posterior distribution under the model of the gradient of the log joint. Okay, so you know that the log joint is easy to work with. You've dealt with this already. When have you dealt with this with respect to model parameters? Unfortunately, the part of homework 3 which more of you didn't do than did do, which is very unfortunate given what we need to know about it, which is Hamiltonian Monte Carlo. Okay. But anyway, the point is, so long as we can approximate expectations with respect to the posterior distribution, which is basically what we talked about, right? We can approximate the gradient of the marginal likelihood. And maximum likelihood parameter estimation can be done by gradient descent of the evidence using the gradient of the evidence with respect to theta. Okay, fine. So it might not be super obvious why this equation 2 holds. So let's just look at it for a second, right? So if we work backwards and we write out what this is, the expectation under the posterior distribution of the gradient to the log joint, we break the log joint into the evidence and the posterior, right? And then we could move the expectation in both cases, right? So there's no x in this term, so that's just the grad of the log evidence. And this term, just like when we talked about it in BBVI, is 0, because when you look at this term, this is just the integral over the posterior distribution of the gradient of the log posterior with respect to the parameters, right? If you use the gradient of the log is 1 over this times the gradient of the original, then that's that step right there. You move the gradient out, this integrates to 1, so this whole term goes to 0, just like we did before, if you remember that. What we've done here is just to verify that the gradient of the evidence can be expressed in this form. Okay, that's pretty cool. So this last setup, like this equation, gives us a handle on how to do model learning, right? Writ large, right? And notice that this has nothing to do with IID examples or Bernstein von Mises or anything like this. This just says there's some program, there's some data, there's some X's, that's it, right? We don't even have to invoke the law of large numbers here. We're just going to do model learning in this particular way, right? And it suggests a pretty straightforward algorithm, which is you start theta somewhere, right? And you loop over some number of iterations, and then you run your favorite inference algorithm. You've got a bunch of them now, theoretically, you know, Metropolis within Gibbs, Hamiltonian Monte Carlo, sequential Monte Carlo, importance sampling, whatever, and you get samples from the posterior distribution at the old model parameter iterate. And then you update theta using some sort of Monte Carlo estimate of the gradient, right? So we have a bunch of samples of X. We can plug them into the log joint, take a gradient for each of those samples, add them up, and then do some sort of stochastic gradient descent on that. Okay, so this is an incredibly general purpose way of doing model learning, right? Semi-supervised models fall into this, unsupervised models fall into this, neural network training falls into, like literally everything falls into this, right? Latent variable models, not latent variable models. This is the way you do model learning. Okay? This is the basis of EM, if you're unfamiliar. This is effectively the EM algorithm, right? With one small exception, which we'll get to in just a second. So if you've heard of EM, then what we're talking about is one step away from being EM. Okay, so let's just look at it again, right? So we're saying, great, this is the thing that we want to ascend. We want to do gradient descent on this. How do we do it? We do Monte Carlo approximate stochastic gradient descent on the right-hand side, where we draw our samples using a posterior inference algorithm. And then we compute Monte Carlo estimates of this gradient. Right, this is important, folks. If you this is critical.
Can I ask, just checking my understanding, because this is sort of the way I'm understanding it, is that we can avoid having to integrate out this X by noticing that this thing on the right hand side inside the expectation is an unbiased estimator of the gradient if we were actually integrating out the X?
If somehow you could magically analytically integrate out the X, which only happens in the few examples that you saw at the beginning of the course in homework 1, right? Then indeed you could just directly operate on the left-hand side in the analytically marginalized version of the model.
Yeah, so I'm saying that this is like, the reason we do this is because it allows us to avoid having to integrate
analytically,
which is most of the time too difficult.
Which is most of the time not possible.
Right. So then is this, and then this thing on the right-hand side inside the expectation, that's in optimization, we would call it just unbiased estimator of the gradient?
That's an unbiased estimator of this gradient. Yeah.
Okay. Yes,
100%. Another fun place for stochastic gradient descent, right?
Mm-hmm.
Yes. Okay. So those of you who have been paying attention, what are the issues with this straight away? And how would you fix them? I want you to figure out what.
Sampling from the posterior.
Oh yeah, sampling from the posterior. That's hard. If we could do that already, we would have solved we've already got the posterior, we've already got the model, we've already got, like, that's a hard problem, right? That's the whole, like, that's nasty, right? So how do we fix it?
We can approximate it.
How? You're not supposed
Well,
to
now
answer. You know the answer, sort of.
All right.
We will know the
Should I
answer.
not say? Should I not say it then?
No, I want somebody else to come up with it. Like, somebody's going to invent EM here. They're not even going to know they're inventing EM.
What does EM stand for?
Expectation maximization, which is not terribly surprising given that what we're doing here is there's an expectation and we're maximizing it. How do we fix it? Okay, so drawing samples from this sucks. It's slow. We don't know when it converges. It's bad.
We can use self-normalized importance sampling.
Oh, thank you, Jason. It's the only thing that I know how to do. It's importance sampling. Okay, great, cool. But we'll get there in just a second. So, so this procedure for model learning is super, super general, right? So this procedure has exactly the same requirements as black box variational inference. So you can take the grad here, and that means basically in our models we have this breaks down because it's just the product over all of the link functions. And the link functions can take theta in them like this, which means, Naomi, this is the continuously optimizable part of partially specified models, right? If you can do the exact same thing, the exact same setup, but you can't use gradient descent for a model for optimization if you put in here combinatorial components of the model as well. Okay, cool. But yeah, to Jason's point, right? Like, let's engage in a little bit of wishful thinking. Let's imagine that we have some magic importance distribution, right? Qx given lambda, right? Then, yeah, cool. Then we would really want to use that instead of doing posterior inference before we take every stochastic gradient Monte Carlo integral step, right? So this is my favorite trick, multiply by 1. This is the same thing, right? Totally fine. Of course, we can't actually compute this weight because we still don't know the posterior estimate, right? So what do we have to do? Well, we have to do self-normalized importance sampling. So this thing clearly comes out, but that is just what's left over when you turn the joint into the posterior, right? Now we can actually operate on this. Right? So this is fairly cool. Okay, so let's see. Let's make sure that you can read this and make sure we know what's going on here. All we've done is gone from equation 2 all the way back here, right? And made an importance sampling version of this. And notice that the gradient has already been passed in here, so this is sitting outside the gradient, so we can do stuff with it. That's no problem. Okay. So we've made an importance sampling version of this with some Q, and then we've operated on this and pulled out a normalization constant, right? So the gradient is still in here. That's totally fine. We don't have to worry about taking a gradient of these terms, right? Yeah. Okay. And we know from self-normalized importance sampling that our estimate of this, right? The normalization constants, the evidence is just the sum of the weights. Cool. All right, fine. This is not an unbiased estimate because 1 over 1 over W is not convex. So f of W 1 over x is convex, which means that you can apply Jensen's inequality to this estimator, and you get that the expected value of 1 over the normalization constant estimate is greater than or equal to the true normalization constant. So this is a biased estimator of the gradient, okay? But we still use it anyway, all over the place, okay? All right, fine. So let me just say this when we get here. Yeah, so I think this is, we'll leave this. So we've got a little bit of an issue, and this is what we're going to sort out in the next few slides after we have our break, which is this magical distribution Q, right, doesn't have any dependence on the current model parameters, right? So this thing is not actually realistic what we're talking about, right? We've got some magic posterior distribution estimator here that theoretically would work for all theta, which is just not true. Right, so lambda has to depend on the model parameters in some sort of a way. Okay. So that is that will come next when we rejoin at 4:40. And we're back. So we have this magical distribution Qx given lambda, which doesn't really make a lot of sense for the purposes we were talking about. Earlier in the class, we talked about the BBVI variational, about BBVI variational inference, which minimizes what we call the exclusive or mode-seeking KL divergence. We just talked a little bit about it last time as well. So we have this KL divergence between Q and P, and that's the form, and we'd like to find the Q that most closely matches this posterior distribution, lambda, in terms of lambda. But we know that this is very difficult to directly minimize, so we did the variational inference thing. So we don't have to do this again. We did this at length, but this just is the exact same thing again. We set up the elbow. We know that the elbow is a decomposition that when we maximize the elbow, we are minimizing the KL divergence because the evidence is fixed. So we maximize the elbow, evidence is fixed, minimize the KL. Great. So if, again, and this is an interesting optimization problem because it's a little bit like a minimax game that's being played, right? So the point is when we were doing this evidence lower bounding thing, right? We were looking at this from the perspective of minimizing this KL divergence. But we can also seek to simply maximize the elbow with respect to theta, which will drive this up. It'll do something to this. Who knows what it's going to do to that KL, but it's going to drive this term up. Right? For a fixed value of lambda, all that we're going to do is end up driving this term up if we optimize with respect to theta, the elbow. Right? So we can also use the elbow, and this is important, as an objective for model learning by maximizing the marginal likelihood with respect to theta as well, right? So let's pretend again that we have this yet another even more special version of Q, which is infinite capacity blah 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 Q star, for which it's possible to exactly match the posterior at a particular value of even all values of theta, but at a particular value of theta, right? And provided that lambda is a function of theta, so on and so forth, that it always matches the true posterior distribution, and we can get that value of lambda immediately, right? Then because the true because if this KL is 0, then we're actually sampling from the posterior distribution. Then our importance sampler is actually sampling from the posterior distribution, in which case we're actually directly maximizing the evidence. Okay. Fine. So, cool. One more thing and we're almost there. So, when we're doing model learning, what we're ultimately going to need to do is actually learn this posterior distribution and the model at the same time. Otherwise, we can't do anything. And it really only makes sense when you have a collection of observations that you'd like to use to learn the model. So if we have a bunch of data from some true distribution, they're IID observations, which we'd like to use to fit our generative model, which has some latent variables, and we assume that our generative model factorizes in this way, then if we make our inference network factorize in this way as well, so in other words, there's one inference network for every observation, then this is important. The elbow also factorizes, okay? So there's a wall of text here, but it's very simple actually what we're after here. We're saying that here's the elbow, this is the elbow. And we're going to operate, we're looking at the IID setting now, where now we have a whole lot of Ys and we have an inference network for each one of them, okay? So if we just write down what this looks like, we have an expectation over a product of Qs, of a log of a product of joint distributions over a product of proposal distributions. And if you write out this expectation in terms of all of the integrals and you start factorizing bits out, what you'll get is basically a collection of individual elbow terms. So in other words, there's going to be an elbow, a lower bound, an evidence lower bound for every single IID data item, okay? So this is the joint probability of data item. This is a proposal for that particular data item, where very specifically here now we've made lambda a function of the observation and the variational free parameter phi, okay? Right. So for large data in the IID setting, the overall model elbow decomposes into a sum of individual elbows. This is important. A lot of people skip over this and don't understand it, but that's important. Okay. Then when we do model learning or inference network learning or so on and so forth, right? Then we can think of this as, again, another SGD style thing, where we can think of equation 22 as being a constant factor away from the empirical approximation to the expected over the true data distribution variational lower bound. Okay. So VAEs, and when we talk about model learning, whether it's structured or unstructured, so on and so forth, this is the objective that VAEs are seeking to maximize with respect to both the model parameters for model learning and phi for inference network learning, okay? Fine. And in case you care, generally speaking, we're going to do stochastic gradient descent with mini batches of B data items sampled at a time. That I don't know is all that important, and we'll get to this reparameterization, I think, later. I think I want to skip over it for now. So, cool. So we have VAEs now, but we'll come back to VAEs because we're going to do VAEs in more detail. But what I want to get to is this idea of model learning via posterior inference and approximating that expectation using importance sampling from some sort of inference network. There's an alternative way of going about doing model learning, which is worth pointing out right now, and this is really what today we're going to stop on, is that in order to do model learning, we have to compute this expectation. In order to compute this expectation, we have to do importance sampling, and that importance sampling thing, as it's going to turn out, is going to require a lot of reparameterization work. Okay, so but variational autoencoders are modern reparameterized variational inference they're a take on basically an old idea that's been around for a long time called the Helmholtz machine. And the Helmholtz machine has basically the same components as VAE. So a stochastic neural network generative model of observations of the world, an amortized inference neural network that encodes the current observation into a high-dimensional latent vector. The difference between Helmholtz machines and VAEs is the objective used to train the inference network, this thing that we need to do model learning, right? So VAEs, as described jointly, optimize a single objective, the elbow. Helmholtz machines use two different objectives, one for the inference network called sleep and the other for the generative model called wake. And there's a bunch of work out of my group that generalizes this more. Okay. So the original wake-sleep algorithm by Peter Diane, who was the director of the Gatsby unit when I was there, makes use of a combination of real data and data that's simulated from the learned generative model. Okay. The wake phase trains the generative model on samples from the data distribution. The sleep phase trains the inference network using samples from the generative model. And last lecture, we actually talked about the basic structure of the wake-sleep algorithm. So let's go through it. The sleep phase of wake-sleep trains the inference network to match the learned generative model posterior p of x given y theta averaged over samples from the generative model. Okay. So this says we want, remember equation 2, we're trying to get posterior samples efficiently for a particular value of theta so that we can do gradient ascent on model parameters. Okay. We just went over very, very rapidly, we'll return to it, a way of doing inference network learning that allows Q to be close to P at a particular model parameters, so that when we do the expectation, when we compute the Monte Carlo expectation of the gradient, those samples are close to true posterior samples. Another way to do this is to do inference compilation or sleep, which is to directly minimize the KL in the other direction, where we'd like Q to be close to P in this way, and to average over all possible data. Okay, and this average over all possible data means that the objective that we need to train is the objective we talked about last time, which is an expectation over the joint distribution under the model of the gradient of our inference network conditioned on the data, so on and so forth. Okay, I expect there will be questions. Okay,
Can I ask one before we move too far?
Yeah, please. Yeah.
So sleep is you update your approximation to the posterior to minimize that KL that's up there, and
Yep.
wake is you minimize. Sorry, you effectively maximize the model evidence. Is that right?
So let's go back to equation 2. Really, actually, equation. Yeah, it's 6. Yeah.
Yeah. So you
sorry,
update.
this is not right. Sorry, this one. Sorry. Yeah, 7. Wake.
Yeah. Okay. So updating the model evidence. So, right?
Yep.
Yeah. Okay. So why are these called wake and sleep? And this has always been kind of confusing to me. Is there a reason for that? And like, is there like, because there doesn't seem to be a reason for it out? Okay.
No. There's a very good reason for it, right? So sleep is called sleep because, and I mean, I've spent a lot of time with these folks. They're very, very, very bright people. Sleep is called sleep because of this right there. So sleep is called sleep because you are sampling, you're training your recognition network, your inference network, your variational approximation, your proposal distribution, they're all exactly the same thing, using data drawn from your model. So if you think top-down system in sort of a computational neuroscience sense, you have a generative model of the world, right? And then there's actually the world.
Yeah, okay, I see.
Right? And this objective, which you see on the slide in front of you, slide 31, right, where we're sampling from our trained generative model, is something that you would do while you're asleep.
Yeah. You're sort of like replaying whatever your model of the world is in your head.
However you've learned the model of the world, you generate samples from it, and you learn to recognize those samples. You learn to invert that generative model and get a posterior distribution over the state of the world given that observation.
Yeah, okay. Yeah, okay. Yeah, got it.
Okay. But for us, while we're talking about, amortized inference and, forcing you guys to slog through all of this tough stuff with, slides that you'll be able to go back and read, but maybe aren't the best for, talking over in course in the class. The point is that we want to, sorry to flip back again all the way to 2, that we want to do model learning, right? We have some partially specified model, whether it's a VAE or neural network or so on and so forth. We want to learn theta, okay? Let's just keep this in mind. We want to learn theta. We can't directly operate on this, right? Because we have to do posterior inference in order to do this. This sucks. We can't do this. It's too slow. You can do it. It's just really, really, really slow because you have to do posterior inference anew for every single model parameter that you consider. So you're doing stochastic gradient descent, and every stochastic gradient descent ascent step that you're taking, you have to run posterior inference before you can take the next step. For the optimization people, that would be insanely slow, right? So what we said is, hey, if you presto magico, if you had this a crazy variational distribution or importance distribution, we could use this for sampling instead. We just directly sample from this thing. We don't have to run Monte Carlo. We don't have to run an inference algorithm. We just directly sample from this queue, right? Then the question is, how do we train such a queue in a way that because this lambda can't exist. This lambda really has to be a function of theta somehow. Otherwise, it doesn't make any sense, right? All right. But if we have this and we have a joint distribution that we can evaluate, then we can construct an estimate of this gradient. Unfortunately, because we're doing importance sampling, self-normalized importance sampling, we're going to have a biased gradient no matter what. Okay. But we're going to be able to take a gradient provided that we have something. And again, this lambda doesn't make any sense, so we have to make this lambda be parameterized by something. And there's a couple of ways we can do this. The first way is variational inference, which we've already covered, but we can remind. So the only thing that we've already covered variational inference, where we said when we maximize the elbow for a particular model for a single value of theta, we get an inference network that is good in the sense that this KL divergence is minimized. And all we're saying is that when we do joint model learning and inference network learning, if we want to do model learning, then we also have to learn the variational inference at the same time. We have to make lambda a function of theta. And that's what we did right here. So this is just the elbow, and we said in the IID case, now the inference network, the lambda is a function of the data. Okay, so this elbow we can use for model learning and amortized inference because down here we have an inference network which is a function of the data and a function of the model parameters, and we can just jointly maximize this thing. Okay, I skipped over the details of this because there's some nasty details in the Prob Prog context, but in the VAE context, that's exactly what you do modulo a reparameterization, which we will talk on. Not the next lecture, but maybe the lecture after, I can't remember. And then we said, okay, there's an alternative way of doing this, which is actually what we talked about last time, which is to minimize this KL divergence, which is just the opposite, the KL divergence rearranged. And when we do this, we can minimize this for a particular value of theta by minimizing this objective, which is what we did last time. But now we have a two-step algorithm where we have to minimize the KL divergence for a particular model to learn an inference network for that model. And then we use that inference network in importance sampling when we do model learning. Okay, fine, cool. Yeah, let's see. Do we care about any of this? No, I don't think so. You can read about that later. So I think that's it, okay? So the first thing we did today, model learning. We want to maximize this thing. That's what we want. Unfortunately, this involves, sorry. Yeah, that's fine. I'll leave it like that. This involves this, obviously, both of these have theta in them. If we want to do gradient-based stuff, we said, okay, actually we can use SGD, and what was it? We can take a gradient with respect to theta of E under P of X given Y, theta of P of X, Y given theta, right? And then we said, oh crap, we have a problem with this. We have a problem with this sampling. So let's importance sample this, right? So we can do grad EQ X given Y phi of P of X, Y. Okay. Cool. That's fine. Noting that this is the elbow. Okay. So all we're saying is that model learning is maximizing the elbow, which we've already talked about with respect to theta, right? But when we maximize with respect to theta, we also need to update our variational approximation because the variational approximation is learned for a particular theta. So we have a very complex, interesting optimization problem, which frankly, we haven't really, as a field, got to the end of here, right? Which is we need to jointly optimize this thing over theta and phi. Okay. And as we will see in gory detail in the next lecture, the lecture after, optimizing this thing for sort of obvious reasons with respect to phi, except when this distribution is reparameterizable, is hard. So another thing that you can do, there's just straight VI, elbow. Another thing that you can do is wake sleep, where you alternately optimize with respect to phi, E, P, X, comma, Y, given theta, and then step 1, sleep. Step 2, wake, optimize, elbow with respect to theta. And this is just optimize elbow with respect to phi and theta. and you can think about this for X, Y writ large, or you can break this down and get stochastic gradient descent if you have IID data with data with a latent variable per data item, okay? Or what people refer to as local latent variables. So we got model learning. We did SGG plus IID data. That's pretty cool. We've got simultaneous model and inference network learning. We talked about the Helmholtz machine, which is basically the old VAE. We've got wake sleep. I skipped over weighted wake sleep, but it's pretty straightforward. It's actually importance sampling this objective. So our weighted wake sleep is importance sampling this objective to avoid sampling from your model. You sample from your inference network there instead. And that is it for today. I assume that there are questions.
I have a question.
Or, yeah, go ahead.
So the wake sleep is kind of just going back and forth between updating a proposal and updating the parameters. That like roughly.
Correct. 100%.
Okay. I'm not clear on why we need to introduce phi exactly.
Okay, this is a good question.
I guess
What?
phi, the family of proposals.
Yes,
Okay.
it indexes within a family of proposals. So the question is for, if we go back way, way, way back to this, maybe this will close the loop. Where is it? So the question is, what is the shape of the inference network? What is Q? Okay. If you remember from last lecture, we had a shape for Q, which was this very deep RNN, this like polymorphic RNN architecture, so on and so forth, that made address-specific proposals for addressed random variables in higher order probabilistic programs. That was part of amortized inference. We also had, inverse graphical model structures plus neural program stubs, so on and so forth. Those were architectures for Q. In a VAE, the architecture for Q is very straightforward. It's a neural network that maps from the data to the parameters of the latent variable. So you can think of the inference network as, in the VAE, as some link function that goes from the data to the parameters of the latent variable, of a distribution that governs the latent variable, right?
Wait, what's the latent variable in this case again?
In the VAE?
Yeah, or in the equations we were looking at before, because we have x and
X.
y. It's
X.
Okay.
Always X. X is the latent variable from the
Okay.
beginning of the course. X. Jason, do you have like a migraine, or are you thinking, or is this making sense, or are you learning something, or is this just old hat?
I was just thinking about a random problem.
Okay. And was that your headphones were off because you just didn't want to listen to me anymore, or you were listening out of, you're like, I'm done with this?
I think there are animals in my walls. That's what I was listening to.
Namrata, questions?
I'm good.
Can I ask a question?
Yeah.
So the big difference between the VAE style of learning and wake sleep is that in wake sleep, you draw samples from the model as well, and you don't do that in the former case. I should really look over this in a little bit more time, but I'm like, in one sentence, sort of like, what's the big difference between the two?
I'm going to give you two different one-sentence answers. One sentence answer is that in wake sleep, we'll talk about this next time, but when you are optimizing the elbow with respect to phi, which I think is So here's the elbow with respect to phi. When you're optimizing the elbow with respect to phi, phi appears here. So it's very difficult to express the gradient of this as an expectation with respect to q, because you're doing a grad phi law, q right here.
Mm-hmm.
So you don't have a q in the when after you're done with this, right? You get an integral grad q, and then chain rule.
Yeah.
And this is not an expectation, so it's difficult to compute a Monte Carlo estimate. That's the first thing. So we have to do some funny business in order to get around that. The second thing is that the funny business to get around that requires reparameterization or something like that. Mm-hmm. So basically the one sentence version of this is that this objective, the sleep objective, does not require any reparameterization tricks, any reinforced tricks, none of this mumbo jumbo. You just directly optimize. This is just supervised learning.
Yeah. But for the wake objective, you have like an expectation over q, no? Or did I get that wrong?
Yeah, but you're only taking a gradient with respect to theta then.
Okay. Yeah, okay, I see.
So if you take a gradient of this with respect to theta, the only place that theta appears is here.
Yeah.
So all of this is it's just EM. That's all that's happening in all of this. It's just expectation maximization under a different name, right?
So the sleep update makes like intuitive sense to me, as in you want the approximate posterior to resemble the true posterior under your current model.
Correct.
But is there like an actual, like theoretical reason why you would also optimize the sleep objective?
I'm not going to derive it here because I would have to look in the TVO to remember the derivation off the top of my head. But it is an interesting observation to note that the sleep objective can also be demonstrated to be an upper bound to the log evidence. So in fact, wake sleep sandwiches the evidence. So
yeah.
But while the model is moving, that's a little bit complicated. So it basically, is there a theoretical reason to do it? I mean, that's the same question. Is there a theoretical reason to do that? No. Right? This is a unified objective. The other one is not a unified objective. And when the model is moving, it's unclear which one is the thing you actually want to do to get good models at the end of the day. And that is actually what all of the revisiting reweighted wake sleep, the thermodynamic variational objective, AESMC, tighter bounds are not necessarily better. All of that work is all about this question that you're asking, like which is the right way to do model learning.
Okay.
Actually, I do have a question.
Great.
In the semi-supervised setting, how will the objectives for wake and sleep change? Like, do we just add a loss on X?
So this slide is actually kind of important to think about supervised versus unsupervised or whatever, right? The objective that you are optimizing always in all of these circumstances, right? This is what you observe, whatever it is. Y's are observed quantities, period. It doesn't matter where they show up in your crazy graphical model. If you have a graphical model that has plates, some of which are observed, some of which are unobserved, so on and so forth, this is everything that's observed. This is everything that's unobserved. End of story. This may not hold in the semi-supervised case. In other words, you might have to break down the expectations into different sets of expectations where some of the sets of expectations have certain things observed and some don't. Right? But the overall objective that you're optimizing is always in the variational inference case, this one. In the wake-sleep case, same thing. You'll have different inference networks that take different amounts of information here when you have extra supervision. In other words, if you have some sort of a graphical model where you have something like, you have a generative model like this on a per data basis, and this is Y, and these are all X's. Wow, those are really small, but I don't know if you can see what I just said. If you have a bunch of those, and in some instances, you have Y observed and this one observed, and some of them you have this one observed and none of these observed, right? Y is all the stuff that's observed. Y is this, this, and this. And X is this, 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 and this, and this. And it just so happens that you can break this down into, you know, different sets of equivalent plates of observations. Does that make sense?
So how will this, in a probabilistic programming context, how will we resolve the like the addresses of the variables in this case? Some are observed, some are latent.
No problem. It's exactly the addressing transformation that we've given you is it will account for all of this.
Yeah.
Mia? Tony? Payman?
I have another question.
Great.
So this like partially specified generative model, is this like a case where we need HOPL instead of FOPL? Depends.
Not necessarily.
Okay.
So you did the Bayesian neural network in FOPL land, and you could also do small structural components so long as you didn't have like a recursive program induction problem. You could do that in FOPL land as well. For instance, you could very easily put a prior on which activation to use. Like for instance, you could say, do I want a ReLU or do I want a hyperbolic tangent activation in my neural network, right? Or the depth. If you have like a finite number of depths you'd like to consider, those would be structural random variables that you would want to optimize over. And you can either treat those as point estimates again, or you can do inference over them. Up to you. If you do inference over them, then you get an ensemble of neural networks, right? And if you do optimization over them, you get a point estimate. And I would argue that in the case of a finite set of neural networks, that you would want to do inference over the structure, because then you get an ensemble, right? And that's a good thing, right? Anything else? Ryan, you're very quiet today.
Good for now. Thanks.
All right. Thank you very much for your time and attention. We'll see you Thursday.